Hi everyone, it's your SI leader Noora here today to talk to you about hydride shifts. So a hydride shift is a particular type of carbocation rearrangement. Another one you've probably heard of in lecture is a methyl shift, and we'll go over that later. We're starting here with this alkyl reaction with this alkene's reaction with our hydrohalogen. So over here we have a double bond. It's going to act as our nucleophile in this reaction and pick up this hydrogen. Now there are two possible intermediates for this reaction, possibility 1 and possibility 2. I'm going to draw both of them out for you here. The first possibility, your hydrogen adds on this part of your double bond, producing electron deficient region on this carbon over here. And your second possibility is an addition of hydrogen at this point, producing your carbocation species at the very end over here. Let me darken this for you. So which carbocation intermediate will our reaction proceed through? So our reaction is going to proceed through our more stable carbocation intermediate. Just looking at these two, we have one that is attached to two different carbon atoms, so this will be considered a 2' carbocation, and this one which is attached to only one other carbon atom, so it would be considered a primary carbocation. And just based off of rules of hyperconjugation and Markovnikov regioselectivity, you're going to continue your reaction through this intermediate. This is going to produce your major product. So I'm going to move on using our most stable intermediate. So what we have here is a 2' carbon, but we can make 2' carbocation, but we can make this more stable. We can make it into maybe a tertiary carbocation, and we can do this through a hydride shift. So there's a hydrogen here on this carbon right next to the carbocation, and what this hydrogen can do is move over onto this carbon over here, producing this species. Now our hydrogen is now over here, and again, trace formal charge, you'll find that this carbon is electron deficient and your carbocation is now here. And you still have the original hydrogen from the reaction right there. So what happened here is our hydrogen from a neighboring carbon moved over to the carbocation, shifting this region of electron-rich sigma bond region onto this carbon over here, producing what is now a tertiary carbocation. So we increased our stability. Now hydride shifts will only happen if you're going downhill, meaning you're going from something that is higher in energy to something that is lower in energy, something that is more unstable to something that is more stable. So in this case, we did that. We went from something that is more unstable to something that is relatively more stable. You'll also find primary going to secondary, and you'll even see sometimes secondary carbocations producing a hydride shift and still being secondary, but being secondary with resonance, which is, again, more stable. Again, it's a downhill process. You'll see that for my hydride shift, I used an irreversible reaction arrow. Once your hydrogen has moved over, don't do anything fancy with your mechanism and try to move it back or move it more than once. It's only going to happen one time, and you've reached your stable species, and we're going to continue the reaction on from here. Again, we had our bromide anion hanging out over here. It's going to come in to that region, producing this final species. So there you have it. There's hydride shift.